some friends on Facebook and some friends on Zoom starting to do that already. Lots of familiar faces as usual. So hello, everyone, and welcome. So introduce yourself in the chat. That is your way to communicate with me throughout the program. So if you'd like to answer or ask any questions, you'll want to type those in the chat. You can respond with our emoji features if you're on Facebook. On Zoom, you can do the same. And we'll go ahead and get started. So we'll be talking about circuits today, and specifically how we can create a circuit using produce. So different sorts of vegetables or fruits was what we mean by produce. So let's go back to our PowerPoint here, and let's talk about a basic circuit. Now, this may not look like a circuit we're familiar with. We definitely don't use potatoes to power up our home, but we really can use them to generate power. Now, in any circuit, you need a source of power. So in this example of a circuit, right, we have the potato, which is actually our source of power. That's actually what's generating the electricity that's going to flow through our circuit. Tell me in the chat if you know any other ways besides potatoes that can act as a source of electricity. So what can act as the source of electricity for a circuit? Think about things we've talked about on Echo Live. Think about things that you use inside your home, right? How do you power up your electronic devices? Where does that power come from? Let's see if we've got any answers. We've got some answers coming in on Zoom. Hello, everybody on there. Go ahead and think about the question. What are some ways that we power up, or how do we get electricity to power up our electronic devices? I'm seeing some people that are saying lemons and oranges. I've never actually used a lemon or an orange to power up one of my electronic devices at home, but if you do, that's actually fascinating. You'll have to tell me what kind of devices you do for that. Someone's telling me batteries. Yeah, absolutely, right? So lithium ion batteries, batteries that we buy at the store, are great sources of electricity. So they create that flow of electrons. Someone tells me cucumbers, lemons. People are naming me all sorts of produce. Maybe these are guesses for things you could use to create a circuit like we're doing today. Someone told me lightning. Yeah, lightning could power up electronic devices, maybe a little dangerous, but definitely a source of that movement of electrons like we talked about during our static electricity episode. Maybe my screen behind me is a little bit of a clue there. People are telling me that great ways to generate these power are things like solar panels, exactly, or wind power like we talked about on Friday during our simple machines lessons. Yeah, so we are naming lots of ways to generate power. And what we're creating for our circuit today is actually a battery that's fueled by this produce. So this potato here is actually acting as our battery. Just the potato itself is the battery, but in any circuit, you also need a medium for that electricity to travel through. So in most of these cases, we use wires. Wires can be inside your device or outside your device if you think about things that have a cord that we need to plug into the wall, right? So in this case, we'll be using electrodes and wires, and those are going to allow electrons to move through our circuit. In order for electricity to flow, right, a circuit needs to be closed. Closed meaning that everything is connected. So if you think about if you put your hands in a circle, right? So if you make a circle, right, this is an example of a closed circuit. A closed circuit would have your electricity turned on, just like a light switch. If you open the circuit, right, you stop that flow of electrons, which is exactly what happens when you turn off a light switch. You actually break open the circuit. So when you move the light switch, it opens up the wires or the point of connection, and so your electricity stops flowing. So closed circuits mean that your circuit is on and functional. Open circuits mean that your electricity is off and has stopped flowing. And then what good would a circuit be, right, if we weren't actually powering up some sort of device? So in our potato circuit today, or in our produce circuit that we'll be building, we'll be trying to power up an LED light. So we talked about LEDs a little bit. LEDs are great for this experiment. If you have one at home and you'd like to recreate this, LEDs work great. We talked about that they only take a very, very small amount of power compared to our other types of light bulbs that we might have at home. So this type of circuit would not necessarily be able to power up a fluorescent light bulb or an incandescent light bulb. They take too much power. But LEDs take only a small amount of power in order for that light emitting diode to start lighting up. And so that's going to be our device in this case. So we've got our battery, we have our wires, and we have our electronic device, which is the LED in this case. So let's go ahead and we'll start setting up one of these potato circuits. Now we said that these potato circuits are generating a flow of electrons, and the potato itself actually does that. Inside a potato, there is an electrolyte. We know that we need to drink lots of electrolytes because we depend on them for our human body processes. Salts are great examples of electrolytes, and potatoes are just full of them. So when we put electrodes inside these potatoes, the electrons will actually start to move between those two electrodes. But what are we going to use as electrodes? We have some copper here. So I have some copper plates. But if you don't have copper plates at home, you might be aware that we have some coins that are made out of copper. You don't have copper electrodes like these at home. You can use pennies. So pennies are copper colored and they are coated with copper, but only if the penny is older than 1982. So in about the middle of 1982, they stopped coating pennies with copper, and so they don't work after that. So if you'd like to do this at home, dig through your old change drawers and try to find some pennies that are from before 1982. And so we'll be using copper as one of our electrodes, and then we'll be using zinc as the other. So zinc is this kind of grayish metal. But again, if you don't have zinc electrodes at home, you can use something else that's pretty common, which are zinc nails. And so I have some galvanized zinc nails here. These galvanized nails are coated with zinc as well. And so we have to have both of these kinds of electrodes, right? Because we're looking for that flow of electricity. For example, if I were to take two copper electrodes, copper and copper, right here in the same potato, right? These electrodes are the same. There's no difference in charge between these two electrodes. So if these electrodes are the same and have the same charge, our electrons won't move. They don't need to, right? We've talked about diffusion a couple times. We've talked about the tendency for things to flow from an area of high concentration or high pressure to an area of low concentration or low pressure. So if we want the electrons to move between the two electrodes, right, there needs to be a difference in charge between them. So if we want there to be a difference in charge, right, we can't use two copper. We need to use one copper and one zinc electrode. So let's go ahead and we'll replace our one copper with a zinc. And so now we have one copper and one zinc electrode in this potato. Now, just to show that there really is energy being created here, those electrons are moving through the electrolyte inside the potato, causing a flow of electricity. To measure that, right, we do have this device that we call a voltmeter. So we can see that our voltmeter right now is reading 0 because our electrodes are the ends aren't connected to anything. And so we're not seeing any flow of electrons right now, but if we hook up our two ends here, our two prongs, to our circuit, we can see that we're getting about 0.78 or 0.77 volts of electricity. That's pretty good for one potato, but it's just not quite enough to light up our LED bulb, which we have right here. So what we'll need to do is connect another potato into our circuit. So let's go ahead and hook in another potato, right? And so for this one, we'll still need one copper and one zinc electrode. So again, we have a flow of electrons between those 2 points. Let's take another look at our voltmeter here. Check that we have movement of electrons. And there we go. We still have about the same amount of power being generated by these two potatoes. So the electrons are moving around, and that gives us about 0.76 to 0.78 volts of electricity per potato. So let's talk really quick before we hook these two potatoes together. Let's talk about the direction that these electrons are flowing. We say that copper is an anion, meaning that it is positively charged. Zinc is the anion, and so it is negatively charged. When we hook these together with our wire, even when we put our device in the middle, we can see that the electrons will flow from negative down the wires to positive. If you'd like a trick to remember this, my favorite science picture is right here, and it tells us that cations are positive. If you're a cat person like me, you'll remember this one forever. So that copper is our cation. So remember, copper, cation, and cations are positive. So they actually accept the electrons because our electrons are moving from an area of high concentration on the zinc to an area of low concentration on the copper. So our electrons move between them and travel around this circuit. Once we go to link these things together, right, we need to hook them in series. And we'll come back to this picture once we hook up our potatoes in series. In series means that we're going to hook them in a straight line. And so they're in a continuous path. Instead of hooking them kind of in a directional unit, we're going to hook them kind of as in a straight line using these clips or these alligator clips here. Now, if you don't have alligator clips at home, you could use any sort of conductive wire that you might have. Make it easiest just because you're actually able to clip them onto your electrodes here pretty easily. But you can always hook them with paper clips using any sort of conductive wire. All right, so we've got a copper to a zinc. So to hook this potato to the next potato, right, we always have to go opposite, right? So we can't hook a copper to a copper because, again, there's no flow of electricity between them because they're the same. So we'll need to hook zinc to copper. And then let's measure the current flowing through just these two potatoes. So we've got copper being hooked to our voltmeter and then zinc being hooked to our voltmeter. And you can see that since we've added them in series, we now see about 1.25 volts of electricity. So some amount lost in our wire due to resistance of our circuit here. But since we've hooked them in a straight line, copper to zinc, zinc to copper, copper to zinc, zinc to copper, through our voltmeter here, right, we've nearly doubled the amount of power that we're generating. So if we want to hook in one more potato here, this time let's try using our alternative. So instead of using our electrodes, I'm going to use this one just to poke a hole. But instead of using our electrodes, we're going to use our 1967 penny as one electrode, our copper cation, and then we'll use our zinc nail as our anion. So we'll take another alligator clip here, connect our zinc to our copper, and let's take a look at the voltage we get now. Turns just so I can see. I'll show it to you in just a moment here. And we're getting about 2.5 volts. It's a little dark and hard for us to see, but let's see if we can get that to balance again. See right there, maybe. We're getting a good deal of power there, almost 2.5 volts. So now let's add in our device. So we'll need to add our LED light, which is the device that we're actually trying to power using this circuit. So we'll attach our alligator clips to the ends, and then LEDs are directional. So it's important that when you hook in an LED, you look at the two prongs on the bottom. They're very, very small and very thin here, but one is slightly longer than the other. And the longer end of the LED is the positive side. So you know that you would need to hook the copper on there. And then we'll hook in our zinc electrode, and we can see that we're actually lighting up our LED bulb. If we open the circuit, our LED turns off. We hook it back together and close the circuit, our LED turns on. Here we go. So open circuit, closed circuit. Open circuit, closed circuit. So even though closed sounds like a bad thing, closed, right, remember, means that we have a closed or completed circuit. And so the electricity is flowing in series through all of our potatoes, causing our device to power up. All right, let's pause and see if we have any questions. So if you do have questions about our potato circuit or how you might be able to recreate this at home, go ahead and tell us in the chat. So we've got another experiment to try, or another device or another source of produce power that we'll try next. But if you have any questions about what we've tried so far, go ahead and tell me in the chat. Someone asks, can you do this with any fruit or vegetable? In theory, yes, right? So any fruit or vegetable that has electrolytes inside it, so something like a potato or a lemon work really, really well because they have lots of electrolytes in them. If you're looking to try this at home, right, you can try other fruits or vegetables. Maybe try an apple and test the electrolyte content of that fruit or vegetable, right? So if you'd like to turn this into an experiment, right, we've talked about this on Echo Live lots of times. All you need to do is change a variable. So we've gone over the setup for a potato circuit. We know that the process works with potatoes. We'll try lemons here together, but if you'd like to recreate this at home, make sure that you try a different variable. You can either try powering a different type of device, something other than an LED. You could try a different fruit or vegetable, try a different type of conductive wire or a different type of electrode, but only change one variable at a time. Melanie asked, will the electricity cook the potato? No, it won't. So really the electrons are just passing through it. If you wanted to cook a potato with electricity, you'd need a whole lot of power. Between these 3 potatoes, we only got about 2.5 volts of electricity, but really there's not much current flowing through them. So we talked about during our high voltage episode that voltage really isn't what's dangerous in an electrical circuit. It's really the current flowing through it, or the pressure or the force of the electricity. So we can actually measure current through this circuit as well. So if we connect our voltmeter here, which doesn't just measure volts, but if we connect it, we can see that we're only getting about 0.2 milliamps of current flowing through this circuit. So 2.5 volts, but only 0.2 milliamps. And so it's not a whole lot of current, just enough to power up our LED, but not enough to cook the potato. Someone asked, can we still eat the potato? Unfortunately, I wouldn't. Maybe if you were to be sure to clean your potatoes or clean your pennies and nails before, and so you know that they're clean, there'd be nothing wrong with them. I didn't do that with mine, and so these potatoes I'm probably going to say are non-edible at this point because they've been used for science. You never want to eat something that was part of a science experiment unless you know it's safe to do so. So if you would like to keep your potatoes after, which I totally understand, make sure that you wash off all of your electrodes because they will go inside the inner part of the potato, the part that we eat. And so you could eat it if you make sure everything is washed and cleaned beforehand. Someone asked, how can you watch these videos later? We do post these videos as soon as Echo Live is done every day. They get posted on our Facebook page. They also go on our YouTube channel as well. So if you search for the Michigan Science Center on YouTube, there's a complete playlist where all of our Echo Live videos end up. So if you're looking to share those links with a teacher or a classroom or another family member, you can find those either here on our Facebook or on our YouTube channel as well. I'm getting a lot of great suggestions for people are asking, do carrots work? Do bananas work? And I would say try it at home. I know that bananas do have electrolytes inside them. They've got lots of potassium, which is one of those electrolytes. And so bananas could be a really great way to try this at home. And you don't necessarily need to waste them, right? As long as you make sure you clean your electrodes first. All right, so let's try our lemon circuit next. If you have more questions, keep typing those in the chat for us. We'll keep coming back to those. But let's try our lemons here, and let's see if we get more or less power using our lemons. So let's go ahead and we'll zoom in so everyone can get an up-close look. And let's start with just one lemon. So if you remember our potato, right, we got about 0.77 or 0.75 volts out of one potato. So let's go ahead. We've got a copper and a zinc electrode. Remember that our electricity is flowing between them because they are different. Our copper is our cation, positively charged, and zinc is our anion. Let's see if I can pan down just a little. There we go. And then let's use our voltmeter again, and let's measure the amount of voltage, not amperage, voltage flowing between them. So here we go. We've got, make sure everyone can see. And in this one, make sure we get an accurate reading. It looks like it's jumping around a little. Maybe I need to stop moving my hands so much. I wish I could get our voltmeter to balance. Maybe I'll use our lemon. There we go. And it seems like we're getting a little bit less power. So about 0.67 volts in this lemon. Let's set up our other lemon just to double check. Got our zinc and our copper. Go ahead and we'll use this lemon this time as our kind of rest for our device. And we're getting about 0.71, so almost an equal amount of power. Lemons are really, really acidic, right? And so they're actually doing a really good job of causing those electrons to flow. Let's hook them together in series, right? So that means we need to go from copper to zinc, and then we'll hook the rest of it together. And we get about 1.37 volts just between these two lemons, which is pretty good. Just two lemons, right? Gave us 1.37 volts. Very lastly, I did a little bit of setup before this program, and I hooked together a bunch of lemons. Let's see, I didn't even count, but I hooked together 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lemons here on this tray. And let's see what kind of reading we get off of this. So we'll grab this lemon and use it as our voltmeter rest. There we go. All right, let's see what we've got. So we've got alligator clips coming off the end. Got our zinc hooked in and our copper hooked in. And with 10 lemons, get a good reading on here. Maybe I'll clip it to make sure we have a really nice accurate reading. There we go. We've got, it keeps fluctuating here, but we've got 5.5 volts of current. Now, the longer they sit in there, right, our electricity, just like any battery, is starting to run out. Now, when I hooked up this lemon circuit about a half an hour ago, I had almost 7 volts. So just like any battery, right, as the chemical reaction inside the lemon takes place, right, we start to use up those electrons. The power starts to run out. So remember that we don't want to leave our batteries and devices when we're not using them, right, because that chemical reaction inside will start to run out, and then we won't have any more movement of electrons or power being generated. All right, let's see if we have any last questions before we get to our very final demonstration here. So we can see that we made about 5.5 volts using these lemons, which is a good deal. I do have an LED, different kind of LED here. This one's a little bit more powerful. This is what would go in inside a car light. Let's see here. Hook in our LED, and then zoom in just a little so you can see. So it might be tricky to see, even though it is. Remember that LEDs are directional, so we need to make sure we're hooking it to the right side. It's kind of tricky to see on camera, but we do generate enough power out of this, but not enough power really to power up our devices at home, right? So anything kind of bigger than an LED, right, requires a lot more power. Now, if you were to want to accomplish this with lemons, right, you'd need a lot more lemons because we know that we're hooking them in series, right? So with every lemon we add more voltage to the circuit. If you think back to our high voltage episode, I do have this device right here. This is that transformer that's able to take 120 volts out of the wall, send it through some copper coils, which then turns it into about 6,000 volts of electricity. That would take a whole lot more lemons than I could ever generate here. But what we can do with this amount of power, right, is we'll show you just how dangerous that amount of voltage or electricity can be. Now we talked about that this stuff is, this device is pretty powerful. So to be safe, I do have some rubber gloves here. These act as insulators, which protect me from the electricity, just in case, right? We're always gonna make sure we're being extra safe. We should never ever play with electricity at home. Try to build these potato circuits, right? But remember that electricity can be dangerous if we're not acting or following safety guidelines. So I'm always following safety guidelines here. We'll go ahead and unhook our electrodes. So we've got, just like in our circuits, we have two different electrodes. We've got a negative and a positive here. Make sure we get our wires nice and out of the way. We'll turn on our device and let's see just how dangerous, though, some of this electricity can be, right? Even if we bring these electrodes near each other, we can see that this is powerful enough to actually start a small fire. So this is a good example of why we should never play with electricity at home. So I have steel wool on the table, and a lot of things inside our houses, right, are conductive. So we always need to be sure that we're being careful with electricity, because we can see that having this electricity too close to our steel wool is actually enough to generate a small fire right here inside our studio. So always make sure we're being safe. We're never playing with electricity at home. And we're always following safety guidelines and asking parents or adults for supervision and help with any of our experiments. So that's about all the time we have for Echo Live today. As always, we're going to take just a moment here to thank our sponsors like Denso, who allow us to bring these programs to you at home every weekday at 2:30 p.m. We're not done talking about electricity. We've got a lot of other fun projects and activities planned using electricity. Later this week, we'll talk about how electricity and magnetism are linked. So stay tuned. We hope we'll see you back here tomorrow at 2:30 p.m. Eastern. If you'd like to be notified when we go live every day, make sure that you like and follow the Michigan Science Center's Facebook page. You can also subscribe to our YouTube channel to make sure that you're seeing when we go live every day. And we hope that we'll see you throughout the week and every weekday after that, while the Michigan Science Center is closed to the public. So thank you everyone so much for joining us for another episode of Echo Live. We'll see you back here tomorrow at 2:30 p.m. Eastern. See you later.